And welcome back to the last video of homework 5B. It's become quite involved here. And what I've done is I teed up 544 here. Okay, so we have question 544. We have went out and I grabbed the data for the problem. Okay, so if, this is just a screenshot what I got right here. All right. And so I took a screenshot and when you actually get to the problem, you have to download some of these things. You can take a look at the tables and, you can click in the table and download it. And this is the data, okay? So it's pretty much all you need. The idea here is follow what I do here. Read the book, follow what I do here. I'm just doing what they say to do in the book to be able to get through this, okay? All right, so we need to do, there's a little bit in here. We have to unpack it, okay? So we're going to do a chi-square goodness of fit, okay? What it's saying is, should we treat this data, this data, should we treat it as normally distributed? Is it? Okay, so we're going to use the histogram function. We're going to use interior bins of width 100 and let the first bin extend up to from negative infinity to 100. 100 to the width. So the points of the value between 0 and 100 we'll get in the first bin. Between 101 and 200 will be the second bin. Okay, that's a histogram, is putting things into bins. It's actually a form of recoding. Let's use a good word for this. Okay, so we're going to recode the raw data into bins. That's what a histogram does. All right, and so between negative infinity, anything else we need here? Note for the. Okay, so later on we're going to have to worry about this numbers of degrees of freedom to do the inverse chi-squared right tail. That's what the RT stands for. Okay, let's not worry about that yet. Let's get through the other parts. Okay, so what I did was prep here from the problem given. There's these class limits from minus infinity to 100. Okay, is the first bin. From 101 to 200 is the second bin. 201 to 300. So this is the human words part of this. And it says anything above 600, we're going to treat as more. That's sort of the nomenclature in histogram world of Excel. Anything above 600 is a catch-all. Because often when we're talking about these distributions, the histogram, it knows that we're thinking distributions. We want to see what the distribution is. The tails have very few things in there. So they've put a convenience in here when we build the histogram to say, yeah, anything bigger than 600 there. Okay. Now, as an input to the histogram function or operation within Excel, which comes underneath data and data analysis add-in package there, okay, it needs a little table. This is the Excel version of what we put in human kind of form over here, okay? Anything up to 100, it's going to count and put the count of what's all the values that have a value of negative infinity to 100 here, 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 here. Okay, so we're going to tell it where to put this. Okay, so what we need to do is go to data, and we're going to go to data analysis, and we're going to go to histogram. Okay, so I think, how's this set up? So the input range I happen to know is correct, but I'm going to do this anyway, all right? So let's grab the data that we need. So this is service time at an airport, whatever that means. So service time, and these are minutes, I suppose. Could be seconds, I'm not sure. Boy, I hope it's not 358. I don't know. All right, so how do you grab all that data? So we grab the first cell, we hold Control, Shift, and down arrow. We'll grab everything in the column, all the active cells. Anything with cells, it'll grab all that data. There are no empty cells in this, okay? So it put it in here. If you notice, it went from A2 to A13, so that worked. So the bin range, where do we want to put the bin? Okay, so we're going to put it in, excuse me, that the bin range is us telling it where the bins are. So the bin range here, I'm going to go through this again with you. So Control Shift and then hit the down arrow. Now I'm on a PC. I don't know what happens on a Mac. I'm just afraid to say. Just look up keyboard shortcuts under YouTube and get a good YouTube on it. All your keyboard shortcuts. All right. So we have, F2 through F7 are the bins. Okay. And we are going to say everything's fine. We don't have a label there. We put the upright range. We don't want any of these other things. And say OK. Boom. Okay. So we put it right here in the G column. So here's the bin. Okay. So what I'm going to do is move that. In fact, let's Control Z it. Okay, can't. Let's delete it. And I'm going to remember to go to G1 this time. Okay, I'm just going to do that again. Data analysis, histogram. Boom, everything's good. The output range I want in G1. Okay. Just want that moved. Boop. All right. So our test, what we're doing, let me get rid of one of these. That one, delete. Okay, so it gave us a graph. It gave us a graph. Okay, everybody, heads up on this, right? We're going to go through the motions on this, right? We're testing to see if this data is normally distributed. Okay, pretty much the histogram picture tells us it isn't, right? It's actually looks like it's more like exponential that we might want to take a look at in problem 545 coming up, okay? So this should point out what this is all about. It's like a 3 miles out. We're going to test this data, and it's obvious that this is exponential. This is not apparently, even by eyeball here, normally distributed. So this should fail the test, whatever test we're running here. But let's run through the paces here. Let's see what goes on with this. In the end, it isn't that complicated. When you go through this, as the steps go on, it looks like it's kind of complicated. Okay, so what are we going to do? Well, it wants us to run normal distribution on this data. We know how to do that. We're going to norm.dist it, right? Okay, so let's do equals norm. Okay, what we're going to do here is, if you think about it, I'm going to pen now, okay? Let's suppose it was normally distributed, right? When we do the norm.dist, what it's saying is it wants to know, the norm.dist tells us the percentage under the curve up to a certain point. So when we do it against bin 100, it'll give us the probability. It's going to take the data and it's going to say what's the probability of that data up to 100, and then to 200. It's doing cumulative here, and then 300, then 400, 5, 6, and then rest of world or more is what we called it there. Okay, so let me get rid of all the red turtle that I just drew there. Control Z, 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 Z. Okay, so let's get rid of that. Okay, see, we're just running the norm dist on this data. Okay, so let's type it in. Equals norm.dist, and what does it want? It wants an x value, okay? So we need to give it the x value. Okay, so what do we put in there? Now remember that the brackets, the bins that we set up, that means something. That means 100. Where is 100 in this data? Okay, so 132 would be greater than 100, and look at all these numbers less than. So we counted up how many items were lower than 100, and we put it in here, 453. But 100 means something. This is the number of numbers, if you will, that were between negative infinity and 100. So we need this number. We're going to run x here, and then we're just going to throw in the mean and the standard deviation, but we need those. Where do we get that from? Okay, so here is a gateway we haven't really used too much. You could either calculate it, or we could run the statistics on here. So we could either, I'm going to have to abandon I'm going to have to abandon this formula right now because we don't have the mean and standard deviation. Okay, so we're going to come back to this. First, we need the mean and standard deviation. Now, one of the ways to do that is go to data. So in other words, we could write in here mean, and I could calculate it. I could calculate standard deviation on our data right here, but now we're going to take it up a notch. Okay, so perfectly fine doing that for that equation. But what we're going to do is throw in the descriptive statistics. Okay, and this is what you're going to use really out there. You're not going to keep typing in mean and all that. You're going to run descriptive statistics on something. Okay, so we're going to run descriptive statistics. Okay, so let's grab the data. I'm going to grab the data. Again, I'm going to do Control Shift down arrow, grabs all that data. It selects the data for that fill in the blank area here. Okay. We don't have a label. I didn't select the first cell, so we don't have a label there. Output range would be B1. I'll go along with B1. That's going to put it up here. Oops. Control Z. Okay, good. It saved it. All right, so we're going to put it in B1. And just to do it, this is what you're going to want to do. Summary statistics. I don't think I need anything else there. Okay. All right, now watch what happens here. And it fills in a great amount of information about the data that we just had. There's our mean. There's our standard error. That's not the standard deviation. Okay. Standard deviation is 105. Okay. So you can kind of look at this kind of weird, like if this is normal distributed data and you have a mean of 126, it says the roll off on here is not going to be out until the first standard deviation is 105. So you're going to be 126 minus 105 is you're way out here at 11. This is weird. Your standard deviation is almost as big as your mean. You would think that your mean if your mean was 126, you're thinking about 12. 10% of your mean might be your standard deviation, not almost 100%. So something is not right here, but we already knew that. I was trying to share with you that we have a picture of exponential here, and that's the way these questions roll out. Is they're going to show us that this is going to fail on normal distribution, and then in 545, then we're going to do the same test, only with we're going to test it against exponential. Okay, so let's keep going here. All right, so now we have our mean and such. What else do we have here? We have the median, we have the mode, kurtosis and skewness, range, min, max. The min and max are nice to know. Okay. All right. Sum and the count. Okay, we got all that. All right, so let's come back up here. We're going to try to run the norm.dist. This is the whole point here. We're going to try to run the norm.dist against that with a mean of that, with a standard deviation of that, and we're going to do cumulative. Okay, so which of these do we have to lock down? Where's G2? G2 we want to roll. We don't want that to stick, but we want to have C3. F4 that. We're going to F4 the C7. That comes from our table, sort of a key data. All right. All right. So what did we just calculate? We just said that the point, we're interested in the point 100, right? When our mean is 126. It's not that far away. And our standard deviation is all wacky because it's 105. It's huge. It's absolutely enormous, right? So that you already see the numbers blow up here. Things are not looking very interesting or correct here. So we'll just roll this right down. Okay. And how do we roll that? Stand by for correct. Okay, and so the way that we fix that is let's go and put the max in here. Okay, so this is going to be equal to the maximum, right? Boom, there we go. Let's see what we get here. G8. I put it in the wrong spot. We'll put it in here. Is equal to 67. All right, there we go. All right, and that actually caught that quite well. Okay, so we have this. This is the cumulative. All right, this is the cumulative normal distribution here. All right, so let's play around and clean that up a little bit. Take it home and clean it. How many decimal points? Let's go to 3. They're saying 2 and such down here. Okay, I'm gonna go one more. Show one more there. Okay. So far, so. Okay, so the next step is, since this is cumulative, we'd also like to know for each of these bins, okay, we're using the same principles that we've used before, okay, so I'm going to draw it so we don't have to get rid of it again. So let me draw with red pen. Okay, so we have this, Control Z, we have this normal distribution, and we sliced it every 100. Okay, that's what we've got. Okay, the last bin happens to be a little bit bigger. You just notice there, just for reference, it's not going to make a big deal. But we captured all the last 7 points from 600 to 867 in the bin. Okay, so we captured all that. All right. So what we've done is slice this, and we've picked it up cumulative. So we picked up that, we've picked up that, we've picked up that. What we want is limits here, our little limits that we have. We want to know what the individuals are. So how are we going to do that? Well, we would get this one by taking this cumulative and subtracting this cumulative, and that's all we're going to do here. Okay, so this is the norm dist on there. Okay, and then we're going to do just a bin distribution, I'll call it. All right, so this is going to be equal to this. The first bin is clear. We don't have to worry about it. The next bin is going to be equal to this bin minus this bin. See, we're just capturing the area between the bins, and I think I just drag that down. See what we get there. Okay, so this picked up. We'd have to go push. This picked up this one bin here up from between 5 and 600. Oh, there's only three. There's only 3 points between 500 and 600, right? There's only 3 points. It's a very tiny number out of 812, I think we have. So it's 0.0002. Okay, so the relative area of that was only 0.002, and we have to go to more decimal places to even find this last bin. Okay. Okay, so let's see how good our numbers were here. Okay, so we're going to use our normal distribution predictor here and see how accurate we are. So what we're going to do is have another actual. Okay, so this is actually this is a forecast. Okay, so this is what the normal distribution should say the population or the proportion of each of these bins should be. We're going to go by that. Okay, so this is the proportion, the forecast proportion. How do we do that? We're going to say, well, it said 40% of the area is up to and including 100. So we're just going to take its word at that, and we're going to say there's 40%, and we're going to multiply the number of points we have way down here. Okay. And I'm going to F4 that because I'm going to need that again, right? Okay, so it's predicting 325 and 326 here. Okay, this is set how many points it expects in 0 to 100. Okay, so let's see how many should end up in each of these bins. All right, so we got a little problem there, folks. All right, so this is the actual over here, right? How well did our normal distribution track that? Well, not that great. Let's take a look here. There's our forecast. And let's turn that orange, my second favorite color, right? Okay. So this is the forecast, and that was the actual, all right? So now we're going to do this chi-squared error, okay? So we're going to look at this chi-squared here. We're going to do by hand, square. And it's going to end up in, we're going to use squares here because there's a squaring going on, okay? So what we're going to do is we're going to see how far off we were from the actual. Okay, so the forecast by way of our normal distribution, it forecasts 325 points. We had a whole lot more. Obviously, it's not normal distribution. That's the whole point here. So it's going to be equal to, doesn't matter what order we subtract them in. So we'll go from the actual and we'll subtract the forecast. And we are going to raise that to the 2. Okay. And if you're really good about things, you're going to use parentheses everywhere. Okay. And we're going to look at that as far as a multiple of the forecast. Okay. So now what we're going to do is see relative to the error, how big was the error compared to the forecast? So we're going to say, we're going to need a few parens in here. Okay. So we're going to take, it really doesn't matter which direction because we're squaring things. We're going to take that number. That's our, what's the distance between our actual and our forecast, okay? And we are going to square these, okay? We're going to square this, and then we're going to compare it to the actual forecast, okay? Now, just to make sure order of operations is correct, use all the parentheses necessary to make it absolutely clear, okay? So we'll enter there. Okay, and let's see, I have to lock down a couple of these things. Okay, 2, no, I don't. Everything's good there. Nothing to lock down. All right. There you go. And let's try to normalize the number of decimal places. Okay. So this is kind of interesting out here. Our forecast by way of our normal distribution, said we should have a 0.002, and we ended up with a 0, something much, much smaller. So our forecast, okay, by way of the normal distribution, was telling us there should be a lot more, okay? These are like really tiny numbers over here, okay? But they end up being a big error, okay? So the error is 18,000 times as big as the forecast was out here. We're headed into troubled waters here, okay? Because we know we've got this exponential, and it's going to, we're testing it against the normal. Okay, so what we're going to do is we're going to do I'm going to write it from over here. The chi-square statistic, okay, is what? It's the sum of all those values. You want to be careful, make sure it's picking up the right things. Okay, so we have 18,233. We're almost there. Okay, and the next thing we have to do by way of the book is the critical value. All right, tells us to do the critical value. So we have to do equals the chi-square inverse right tail. Okay, it tells us to do that. Okay, and the probability here is the statistical significance we're going against. Okay, so it told us 0.05 if I'm correct. I think it is it in here somewhere. 0.05. I think we can go by the book. Oh, there it is. So we want to know what the chi-square statistic is. Oh, I'm in the middle of doing that. Okay, so let's finish this off. So the next question we're going to be asked is 0.05. It tells us to use 0.05. All right, and the number of degrees of freedom is going to vary a little bit from how many degrees of freedom. It says 1. We have to subtract 1 plus the number of bins minus 3. So how many bins do we have here? We have 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to put 7 in there. And we come up with a number of 14.06714. So our crit value is 14.06. So the criterion for this test is that the chi-square statistic is less than or equal to your critical value. And we're nowhere near it. We're extremely bad. And you would think that it would be rudely telling us that there's something wrong with this picture because we obviously don't have normal distributed data. And if we go on to 545, we run this again. We'll take a look at it. Instead of running the normal distribution, I'm going to come back. I think I'm going to do it right on this page. I'm going to run right next to this because everything else kind of stays the same. And I will run that under the 545, which is asking, as I mentioned, about running the test against exponential distribution. So rolling right into the exponential distribution. There we go. We're going to do this very same thing we did before. Okay, so we need to do exponential distribution right there. Okay, so it needs an x. That, of course, would be our bin here. We'll go along with that. We'll take that. Okay. And the next thing it needs is lambda. Now, remember, this is service times, right? And I'm telling you, I don't know whether they didn't say whether it was seconds or minutes. I don't think. Okay. So the lambda is just going to be 1 over, we're going to use 1 over the mean. Remember, lambda is the average, let's see, it's average arrival rate, okay? It's 1 over the time. It's frequency. Frequency is 1 over the time, okay? So we're going to use 1 over the mean. Come back over here for the mean. Got it? All right. And the last thing is true. Same kind of thing we did last time, just a second ago, okay? So got that. And we just have to lock down our C3 so we can bring it on down. All right. And then maybe just adjust decimal places so it's uniform. Okay, just like before, what we're going to use is, that's a probability, right? So what we're going to do is we're going to figure out the forecast bin distribution, like what should it be from this prediction here is going to be equal that star the number of items, and we're going to lock that down. All right, so it's predicting 444. Oh, things are looking much nicer now. The actual frequency was 453. It's looking pretty good out of the chute. Bring this on down. And something went wrong. N2 times C15. Because we forgot. Let me move this over. All right. We're going to have to fix this. Misinterpreted my own heading here. Okay, so what we needed to do was the real bin distribution was per, I forgot to do the subtraction here. Okay, so this is going to be equal to this. All right, and how many occur between 100 and 200 by forecast is just going to be equal to that minus that. There we go. Okay, so now we have by bin. This now needs to be O2, not N2. Sorry about that. You can see what I'm doing here. I'm going back and getting that. And I can now drag that down. I could see something went wrong there. There we go. That's much better. Let's just for fun add these up. And it's roughly 812. Okay, so we didn't do that over here. Alt equals. Let's see. $812 it came out to there. Okay. Forecast. All right, now we have everything well. Back and good again. Okay, so I'll make this one orange also. So it pulls our eye toward it. Okay, so now we're going to do the chi-squared. We're going to take this error. Okay, so this idea of this error occurs over and over and over again in statistics to see what you're going to compare, how off you always have to compare. You always have to check forecast versus actual. Okay, so the chi-square is going to be equal to, we're going to go by, I know I need two parens. By this time we've done it already once, so it's going to be equal to, no, not that. It's going to be equal to that. How far away was it from our forecast? We're going to square that and divide the whole thing by the forecast. How far off were we? And grab it. There we go. Let's just make sure that's correct. Yep. The difference squared over P2, okay? Right. So we were almost dead on. We were only off by 17. Our error was 17% of the forecast. And we can pull that one right down. That. Okay. So now let's do our, I could probably just grab these. It's a cheat. Control C. And as long as I end up in the right place, it should work. All right. Save myself a little bit of time. And look what happened, folks. When we ran it against the exponential, our chi-square stat came out less than 14. Okay, so the critical values still didn't change. All right, that didn't change. There's nothing that changes between there. And our chi-square statistic went way down, way down. Look at that, it's below there. So that passes. That actually passes. All right, now a note to you. I probably should mention something way up front about this, that these numbers seem to go into the system, and I'm having troubles getting the critical values. I tried that before, and there's a little bit of discrepancy from information that I have about how to set these bins up. but what we did here, what I showed you here, is exactly what they said here. And what ends up happening is, in the first case, they came up with a critical value, which is a problem of 9.9.5. It's a little bit off from here. The only way to make that go down is to reduce the number, just reduce the number of bins. It isn't working for me. I'm going to square up with you on that, and I'm going to have to find out if there's an actual answer to it. But let's just move on. This is more important: the chi-squared versus the critical value. All right. So hopefully, I'm going to put this out as an email, or yeah, as an email. I'm going to send a link to this video, and I will, in that video, tell you all to watch out for these problems, that this critical value ends up with a little ambiguity about how to run the bins, but we did it exactly how they told us to do it there. Right, so what I did was I just ran over and I grabbed a solution to what our numbers are here. If I do a Control V, you're going to see, okay, so this is 545, excuse me, and you notice that our numbers are a little bit off from theirs. So when we're dealing with these kinds of things, there's a lot of room for rounding errors and such, and I'm not sure these are actually working numbers that I've got, that I'm showing you here, okay? So they claim that the chi-squared critical value was less, was 11.02 or 11.07. Okay, so they're claiming it cannot reasonably be assumed to come from an exponential distribution, but we're really close on this one. These two numbers are so close that, as I said, I'll send this out as an email, as a note to everybody, and see what everybody else gets on this. See whether you come up with the right answer. So there you go. There's a whole big homework 5B. A lot of work there. And we'll talk to you soon. Hope you get a lot out of this video. Bye for now.